Hello, my friends. Brainy Nerd Tutor here, and I'm going to go through a super common problem in physical chemistry. We're going to calculate the molar entropy for mercury. This could be any substance, really, at 298 Kelvin, and we're given some information about heat capacities at different temperatures or states, and of fusion here in the melting point of mercury. So to calculate the molar entropy at some temperature, we need to start at 0 Kelvin here. So we have mercury solid at 0 Kelvin, and we need to heat it up to 298 Kelvin. Now we can't do that right away. First, we need to heat it up to its melting point. Although I'm going to stop at 15 Kelvin because some of you may have learned about something called the Debye law or the Debye extrapolation, the T3 law. If you haven't heard about that, just ignore this term. But if you had, we may need to include this approximation into it. So we'll heat it up to 15 Kelvin. And then once it's 15 Kelvin, we'll heat it up to its melting point, 234 Kelvin. So we're going to do some heating, and we're heating over here. Okay, and now that it's at its melting point, we'll melt. So melting, we'll melt the mercury, so we'll produce mercury liquid at 234 Kelvin because it melts at constant temperature. And now that it's a liquid, we'll heat it up to the desired temperature, which is 298 Kelvin. So heating, and this is 298 Kelvin here. Okay, so the molar entropy of mercury at this temperature equals the change in entropy through all these processes here. Now, there's a lot of processes, but it goes pretty quick. So if we want the molar entropy at 298 Kelvin, that's going to equal to its entropy right at 0 Kelvin, plus the change in entropy that it takes to heat it from 0 to 15 Kelvin. So I'll just say 0 to 15 Kelvin, plus the change in molar entropy when we heat it from 15 to 234 Kelvin. 15 to 234 Kelvin, plus now we want to melt it. So this would be the change in entropy of fusion, of melting. And this is at 234 Kelvin. I don't need to put that. I will anyways. Plus the change in molar entropy from heating it, to 290, from its melting point, 234, to 298 Kelvin. Now there's a lot of terms here, but things work out pretty quick. At 0 Kelvin, the entropy is just 0 joules per Kelvin. It's at 0. Now there could be residual entropy if you're told about that, but otherwise we'll just assume this follows the third law entropies. So this is a third law substance, so it's just essentially 0 joules per Kelvin at 0 K. There we go. Okay, so that one's 0, so that's fun. Now we need to heat it to 0 to 15 Kelvin. Now this is where we use the Debye law. If you haven't seen it, then ignore this term, but if you do have to deal with the Debye law, what it is that it's an approximation of what the heat capacity is at very low temperatures at less than 15 Kelvin. And we're going to add the integral of Cpm over T dt. If you want to know where this equation came from, I made a couple videos about it, so check that out. Otherwise, we're just going to keep on going. So now we're going to heat it up from 15 to 234 Kelvin. So again, we'll use the same integral. Whoops, we're going to go from 15 to 234 Kelvin of Cpm over T dt. And now that we heated it up to the melting point, we want to melt it. And this, again, I've made videos on it. Let me know if you want to see another video or where it is. But it equals to the enthalpy of fusion. This is molar at standard state divided by the temperature. And now we're going to heat it up again. So this will be the integral from 234 to 298 Kelvin of Cpm over T dt. Okay, now I made these CPMs. Maybe I'll make this like a prime and a prime prime and a prime prime prime. These are different heat capacities. Now this is just 0, so I'm just going to ignore that. So if you are learning the Debye law, the Debye law extrapolation says that the heat capacity, molar heat capacity, is approximately equal to some constant times T to the cubed. So if we substitute that in, so it'd be the integral of 0 to 15 of some constant a t cubed over t dt here. Okay, and now we'll keep going. Now the heat capacity of, this is of the solid, because this is as we're heating it up to its melting point. And the heat capacity of the solid changes. If you want, I can go do a video on that showing the derivation of how it changes. This really can't come out of the integral, but based on this question, we're just given a value for the heat capacities, values for the heat capacities. So we're going to assume that the heat capacities are constant in this question, even though they're not. You may make that approximation in class quite a bit, but otherwise, we're just going to pull it out. So this is of the solid here. And we are left with the integral of 1 over t, dt over t. So the integral of 1 over t it's our friend the ln, and it's going to go from t2 divided by t1. Again, this is a change, t2 minus t1, but using log laws, we get it divided by. My previous videos, I've shown that. If you want, just let me know in the comments, and I can do another one, derivation. This one here, this heat of fusion, this we already have data for, so I'm just going to leave it as it is. And then we have the other one where we're going to yank it out of the integral. Even though the heat capacity of the liquid does change with temperature, we're going to assume it's constant because we don't have any other information. This is of the liquid, and it's be ln T2 over T1. All right, moving along. So the integral of this, first we need to divide this by t. So that will be the integral from 0 to 15 of a t squared dt, which is literally 1 over 3. This is the anti-power rule here, a t cubed from 0 to 15. And if we assume that at 0 Kelvin, this term is 0. So this is just 15 at 15 Kelvin. So this would be 1 over 3 a t cubed at 15 Kelvin. I'll just write 50. I shouldn't do a line. At 15 Kelvin. Now we don't know what the a is. This here, this is our CPM. This is the Debye extrapolation. CPM is AT cubed. So it's literally equal to CPM at 15 Kelvin divided by 3. So that's nice. We have a value for that, which is 7.34 joules per mole per Kelvin, 7.34. So this is 7.34 joules per mole Kelvin. That's all divided by 3. Plus, now we have the heat capacity of the solid, which is, now this is all the data we have. We have it of the liquid. It's a solid at 15 Kelvin, so we're just going to use this heat capacity here, even though it does change quite a bit. But we have no other information, so we'll include it. So 7.34 joules per mole Kelvin, and that is from, I'll clean up my 7. Temperature goes from, we're heating it from where to where? We want to heat it up from 15 Kelvin to 234 Kelvin. 234 over 15 Kelvin. Now we want to melt it, and the enthalpy of fusion is 2.29 kilojoules. 2.29 times 10 to the 3 joules per mole. We need to multiply by 10 to the 3 because we're given this value in kilojoules, and here our other terms are in joules, so everything has to be in joules, divided by temperature, and it's melting at 234 Kelvin. Plus, now we want to heat it up. The heat capacity of the liquid is 21.75 joules per mole Kelvin times ln. We're heating it up from what to what? Oh, we're going to 298 Kelvin from 234 Kelvin. All right, so if you plug that into your calculator, 7.34 divided by 3 plus 7.34 times ln of 234 divided by 15, close brackets, plus, what is that? 2.29 times 10 to the power of 3 divided by 234 plus 21.75 times ln. I hope this is all good. If I didn't make an error. 298 divided by 234, close bracket. Oh, I already closed the bracket. 37.657. So 37.65. What is it? 37.65. 37.6565 joules per mole Kelvin to how many sig figs? Looks like we have, well, this is 2 sig figs. Let's give it 3 sig figs. So 37.6 joules per mole Kelvin. We'd round down to 6. If you rounded up to 7, that'd be fine as well. All right, everyone. Hope you enjoyed it. This is going to be different than the actual value because we just assumed the heat capacities were constant and we used the Debye extrapolation. But that's the process. Hope you enjoyed it.